Hi everyone, in this video we're going to talk about division of whole numbers. In the grade 3 Common Core standards, we find that students should be able to interpret whole number quotients of whole numbers. Alright, so starting in the 3rd grade, our students are expected to know how to divide. Alright, so just before we get started, just some vocabulary that you should know. Consider this division problem below. A divided by B equals C. In this problem, A is going to be your largest value, and it's going to be called the dividend. B is called the divisor. This is what you are dividing by. C is called the quotient. And this is the answer. We're going to look at 3 models of division in this class. We're going to look at the repeated subtraction model. We'll also take a look at the set or partition model. And then lastly, we'll look at the missing factor model. We're going to start by looking at the repeated subtraction model of division. This model connects division to the previously learned operation of subtraction, and it views division as the taking away of equal sized sets. All right, so it's viewing division as the taking away of equal sized sets. All right, so let's look at an example using the repeated subtraction model of division. June brought 18 M&Ms to share with her friends. If each friend eats 2 M&Ms, how many friends can June share with? All right, so we've got our 18 M&Ms. We can use what we know about rectangular arrays to verify that this is 18. It's got 3 rows. It's got 6 columns. So we know that this is 18 M&Ms. And we're going to repeatedly subtract off 2 M&Ms, and we're going to see how many sets, or in this case friends, that we're left with. All right, so here's our first friend, second, third, fourth, fifth friend, sixth friend, seventh friend, eighth, and ninth friend. All right, so we can share with 9 friends. All right, and this is demonstrating the division problem. 18 divided by 2 equals 9. Here's another example with repeated subtraction. It says use the repeated subtraction model to solve. All right, so you could use a visual like M&Ms, and you could say subtract 2, subtract 2, subtract 2. That gives us 3 sets, so that tells us that 6 divided by 2 is 3. All right, if you did not want to use a visual, you could also just say 6 minus 2 is 4, minus 2 is 2, minus 2 is 0. All right, so we repeatedly subtract 2 until we get to 0, and then we can go back and count and say, okay, we subtracted 2 1, 2, 3 times. Next, we have the set or partition model of division. This model is based on the idea that the divisor can be thought of as the number of sets that you want to break the dividend into. And your task is to determine the size of each of those sets. So again, instead of taking that problem 6 divided by 2 and thinking of it as 6 M&Ms, and I'm gonna give 2 M&Ms to each friend. How many friends can I give them to? This partition model of division is thinking of it as, okay, you have 6 M&Ms. I want to split those up into 2 groups. How many M&Ms are in each group? All right, so you may also, some textbooks, you'll see this called division by sharing. And our whole goal here is to take that dividend and divide it into equally sized groups. All right, so we have this problem. AJ has 15 t-shirts. He sorted them equally into 5 laundry hampers. How many t-shirts did AJ put in each bin? All right, so we are demonstrating this example here, 15 divided by 5. All right, so we're saying we have 15 t-shirts. We want to split those up into 5 different laundry hampers. All right, so first let's put our laundry hampers down, then our t-shirts. All right, so if you were doing this with your students, you would probably want to sort these one at a time. But since you guys already know the answer, I'm going to go ahead and split these up. So we have 3 going into the first bin, 3 going into the second bin, 3 in the third, 3 in the fourth, and 3 in the fifth laundry hamper. All right, so the set or partition model of division, again, views the divisor as the number of groups that you're breaking it down into, and then your goal or your task is to figure out how many objects are in each of those groups. All right, so here's another example. It says use the partition model to solve. All right, so suppose we have the problem 6 divided by 2. Now previously when we used the repeated subtraction model of division, we just took 2 M&Ms away, 2 M&Ms away, 2 M&Ms away until we had no M&Ms left. But this model says you're going to think of the divisor as the number of groups that you want to split this up into. So if you were demonstrating this to students, you might want to go over here and draw, okay, here's our first group, here's our second group, and then one by one slide these M&Ms over. One, first group gets 1 M&M, second group gets 1 M&M, first group gets another M&M, second group gets another M&M. We already know that the answer is 3, so we're going to divide those into our 2 sets. Each set gets 3 M&Ms. All right, so hopefully you see the difference between the repeated subtraction model of division and the partition model of division. With repeated subtraction, it's telling you just subtract this number every time over and over and over until you get to 0. That tells you what the answer is. Once you go back and look at how many times could you subtract the divisor. With the partition model, you're saying, okay, I'm taking my dividend and I'm splitting it up into however many groups the divisor says. So if it's 2, we're trying to split it up into 2 groups. If we're dividing by 3, we're splitting into 3 groups. If we're dividing by 5, we're splitting into 5 groups. The last model we're going to look at is called the missing factor model of division. This model is more general than what we saw with the previous 2 models. And I think students' goal here, or your goal is that once students have a good grasp on division, then hopefully they're using this missing factor model each time. And the missing factor model of division is where we rewrite a division statement as a multiplication statement. All right, so it's based on inverse operations. Since division is the inverse of multiplication, we can use our prior knowledge of multiplication fact families to identify the missing factor. All right, so here we're just doing a straightforward problem. It says use the missing factor model of division to solve. 90 divided by 9 equals blank. All right, so you're going to start by saying, I'm going to call that blank square. Now, as students get older, as their math knowledge increases and becomes more sophisticated, you could call this a variable. but for now we'll just call it a blank box. All right, so 90 divided by 9 equals blank. All right, so we can rewrite that as 9, the divisor, times the box, the blank box, equals our dividend. All right, so divisor times blank equals dividend. And then students can use what they know about their multiplication facts to solve this equation. So 9 times what gives us 90? Of course, we know that 9 times 10 gives us 90. So now we know that the blank equals 10. We can replace that blank with 10. Now we're going to talk briefly about some whole number division properties, and then I'll also speak about some of the properties that you will not see here. So the set of whole numbers is not closed under division, and we have seen that before. We saw that with subtraction, and we know that this means that whenever you take two whole numbers and you divide them, the result is not necessarily a whole number. Now this is pretty straightforward if you think about it. So something like 27 divided by 9, those are both whole numbers, and when you divide them, you get a whole number. But this doesn't always happen. For example, 2 divided by 4 is 1/2, and that is not a whole number. So even though 2 and 4 are both whole numbers, when you divide them, you don't necessarily get back a whole number. All right, so you'll also notice that you don't see the distributive property or the associative property or the commutative property with division, and that's because those properties do not hold under division. So you have to be very careful when you are dividing, and what we want to take from this as educators is we just want to be extra careful when we are picking out the problems for our students for subtraction and for division. All right, so I would say this is the most complicated thing that we're going to talk about in this section. It's called the division algorithm. Now, this is something that you have been using for a long time. You probably just didn't necessarily see it written this way. All right, so what it says is that if you're given any whole numbers, A and B, with B not equal to 0, then there exists some unique whole numbers, Q and R, such that A is equal to B times Q plus R. Now let me tell you what these letters represent. A represents our dividend. That's that big number. B is our divisor. That's what you're dividing by. Q is the quotient. That's the answer. Little r, you can probably guess, is the remainder. And then there's this extra little piece at the end that seems like it's not super important, but it actually is very helpful. It says that the remainder, I'm just reading, starting from the left here, the remainder has to be greater than or equal to 0. All right, so your remainder cannot be something that's negative. So the remainder has to be greater than or equal to 0, and the divisor has to be greater than the remainder. All right, so that's going to be important in just a second for this next problem we're going to do. So let's just write that out in words. The divisor is larger than the remainder. The divisor is larger than the remainder. And I think that makes sense if you think about something like this division problem, 32 divided by 9 or 9 into 32. If you were dividing this, you would say, okay, 9 goes into 32 3 times. You would subtract 27. Remainder is 5, right? So our remainder is smaller than our divisor, or you could say that in the opposite way, which is how we wrote it down here. The divisor is larger than the remainder, right? So the divisor, what you're dividing by, should be larger than the remainder. All right, so division by 0 and 1 is frequently misunderstood by students, and you may find yourself struggling to explain to students why you can't divide by 0. When you're talking about why, dividing by 1, you can reword that as a missing factor problem. But division by 0 might be a little bit harder to explain. All right, so here's one way that you can try to explain this. Suppose that you're asked to find the value of the expression 3 divided by 0. Of course, we know that this value is undefined, but let's talk about how we would explain this to a third grader. One of the easiest ways that you can demonstrate that you can't divide by 0 involves grouping objects. So, for example, if you had something like 16 divided by 2, you could say, I'm taking 16 M&Ms and I want to figure out how many groups of 2 can I make out of 16 M&Ms. But let's try that with this problem. How many groups of 0 can I make out of 3? How many groups of 0 can I make out of 3? You can't. You can't make a group of 0 out of 3 M&Ms and use up all of your M&Ms. All right, so to divide is to break something into groups of a certain size, and breaking something into groups of 0 just doesn't make sense. Now, a more formal way to prove this involves thinking of this as a missing factor problem. All right, so 3 divided by 0 equals C if and only if there exists some number C such that 0 times C, that's the missing factor. Earlier we drew this as just a little box. So if 3 divided by 0 equals blank, then that tells us that 0 times blank equals 3. And recall our zero property of multiplication that we learned in the last section. The zero property of multiplication tells us that anything multiplied by 0 gives you back 0. All right, so I'm just looking to read the formal definition of that property. All right, so it says for every whole number a times 0 equals 0. All right, so this will never be true, no matter what the value of C is, no matter what we put in that box. There's nothing that would ever make that equation true. All right, so since there's nothing that makes that equation true, that tells us that this expression, 3 divided by 0, is undefined. All right, so in section 3.3, we learned that addition and subtraction were related objects, or related operations. Subtraction was just the opposite of addition. In a similar way, multiplication and division, where you have no remainder, are related. Division is the inverse of multiplication. All right, so consider this diagram, which shows how all of the operations are related. All right, so it shows you here. Let me see if I can get my laser pointer to show up. All right, so you can see here that addition and subtraction are inverse operations. Down here at the bottom, multiplication and division are inverse operations. And we also learned that there's a connection between addition and multiplication. We said that multiplication is just repeated addition. And we also learned today that division and subtraction are related because division is just repeated subtraction. So all 4 of our main operations, they're all related. All right, so the last thing that we need to talk about are our 2 division algorithms. We're going to look at 2 different division algorithms today, using base 10 blocks to develop the standard division algorithm. I like this method, and I think it's fun to see it get broken down, see your dividend get broken down. And then we're also going to talk about partial quotients, or the scaffolding algorithm, and some teachers really like this method. It's definitely going to make you feel a little uncomfortable at first whenever you first try to do this on your own. But some teachers find that this is really helpful for students who do not have all of their multiplication facts memorized and just have some basic multiplication facts memorized. All right, so let's look at how we can use base 10 blocks to develop our standard division algorithm. All right, so let's say that we have this problem, 128 divided by 4. Now, when you are demonstrating this division algorithm with base 10 blocks, you always want your divisor to be smaller. You don't want to have a large divisor, and you're going to see why in just a second. But I'm going to start by just using my base 10 blocks to represent my dividend 128. All right, so I can represent my dividend 128 with a 100, 2 10s, and 8 1s. All right, so that's 128 represented with base 10 blocks. And I'm being asked here to divide that dividend into 4 groups. All right, so I'm going to lay 4 circles out on the table here, and I'm going to ask students to try to equally divide this dividend, these base 10 blocks, into these 4 groups. So that's why you wouldn't want to divide by a large divisor here, because that's just going to give you more and more groups to have to break this down into. So it's going to be better for base 10 block problems if you are dividing by something small, 3, 4, 5, 6, something a little bit more manageable. All right, so I'm going to start with my 100s place. You could start with the ones, but I would suggest starting with the largest group first. All right, so I'm going to move my base 10 block to the middle. I need to divide it equally into 4 parts. Students can now use what they know about money to divide this into 4 groups. 100 divided by into 4 groups. You can think of it as $1 divided into 4 coins. That would be 4 quarters, which would be 25 each. All right, so each group is going to get 25. All right, now I'm going to bring my 2 10s into the middle. I want to break those up equally into 4 groups. I can't do that right now. I need to make them into ones first. So I'm going to take my 2 10s, make them into 21s. All right, so now I have 20 of my 1 blocks. I can break 20 up into 4 groups by giving 5 to each group. All right, so each group gets 5 1s. All right, and then the last thing that I need to do is take my 8 1s and divide them equally into my 4 groups. That gave me 2 for each group. And now I can, you would have students verify that you have the same amount in each group. And let's count up how many of my base 10 blocks are in each group. So I have 2 10s, that's 20, 21, 22, 23, 24, 25. I know that this is 5, so that's 30. And then I have 2 more, so that's 32. All right, so that tells me that 128 divided by 4 is 32. All right, so kind of a fun way to start learning division. I saw other demonstrations where teachers used like fake money, and they said, you have $350 and you want to split that up between your 5 friends. All right, so then students can also practice, what they know about money. So saying like, in a 50, you could represent that as one $50 bill, or 5 10s, or 2 20s and a 10. So there's lots of different ways that you could demonstrate this type of idea when you are motivating the operation of division in your classes. All right, so I'm going to show you our concrete model before we go on, which is how we all learned how to divide. We put our divisor out front, we draw our little division box, and we put our dividend inside. All right, then you're going to look and say, okay, how many times does 4 go into 1? It doesn't. because 1 is smaller than 4. So we go to the next one. We say, how many times does 4 go into 12? We know that it goes in 3 times. Now we're going to multiply. 3 times 4 is 12. We're going to subtract. 12 minus 12 is 0. Then we drop down the 8, and we'll repeat. 4 goes into 8 how many times? Goes in exactly 2 times. 2 times 4 is 8. Subtract again. That gives us a remainder of 0. Alright, so just a reminder, let me switch over to my laser pointer. 4 is our divisor, 128 is our dividend, 32 is called the quotient, and 0 is called the remainder. Alright, so this is probably how we all feel most comfortable dividing using that concrete model. But I'm going to show you one more way that you can teach division to your students. And again, this is great. The scaffolding method that we're about to go over is good for students that do not necessarily have all of their times tables memorized. All right, so the last division algorithm that I'm going to show you today is the partial quotients, or also called the scaffolding algorithm. And you can use this for any problem, but I personally found that a lot of teachers were using this for large dividends, like in this case 2,519. It's a very large dividend, and that's being divided by 12. Alright, so you start this off just like you would the concrete algorithm. Alright, so you set up your little division box. You have the divisor 12 on the outside, you've got the little division box, you've got the dividend on the inside. So I'm just going to move that out of the way because I'm going to need all the room I can get. You're going to see in just a second. Alright, and you can see I made that a little smaller because, like I said, I'm going to need all the room I can get. Alright, so imagine you are teaching division and you have thrown this problem up on the board, and probably your first instinct is to say 12 goes into 25 one time. Alright, but we're going to throw that concept out the window. What you want to ask your students is you want to say something like, how many times can 12 go into 2,519? So you're thinking of it, the dividend as a whole. With our concrete algorithm, we typically think of our dividend and we break it up into smaller pieces, but the partial quotient algorithm, or the scaffolding algorithm, wants you to think of the dividend as a whole. So let's imagine you've posed this question to your students. You've said, all right, how many times does 12 go into 2,519? Well, maybe they know their basic addition facts, and they know that 12 would go into 2,519 at least 100 times, because 100 times 12 is 1,200. All right, so we start off and we're just, chipping away at this problem. So we say, okay, we know it goes in at least 100 times, so let's subtract that off. So 100 minus 12 is 1,200. We're subtracting that. That gives us 1,319. All right, so maybe whenever you do this, then another student says, well, it can definitely go in another 100 times then, because 12 times 100 is 1,200. So you could subtract off another 1,200. All right, so we're going to go in another 100 times. All right, so 12 times 100 is 1,200. Let's subtract that off. That leaves us with 119. All right, so much smaller number now. So now you're asking your students, how many times can 12 go into 119? Now they might say a smaller number. They might know, their 5's multiplication facts. So maybe they say 12 times 5 is 60. We know it goes in. We know 60 is smaller than 119, so you could chip away at it that way. Now I'm running out of room, so I'm going to jump straight to the end. But maybe one of your students says, well, 12, it wouldn't go in 10 times, because 10 times 12 would be 120. So it's got to be less than 10. So maybe a student says, okay, well, let's try 9. All All right, so 9 times 12 is 108. So we're going to subtract off 108. 119 minus 108 gives us 11. All right. So now you know that you can't go, 12 can't go into 11. That's too small. So since our last number here is smaller than our divisor, then that must be the remainder. So now we're just going to combine all of those partial quotients up there at the top. 100 plus 100 plus 9 is 209, and we have a remainder of 11. All right, so I would encourage you to try this with some different numbers. Maybe just change it just a little bit. Do 12 into 3,212. So just change it a little bit and try this out on your own, because this is one of those where if you practice it a few more times, it'll become a little bit more familiar to you, and you'll see, you know, the advantages of it. And again, it's okay to feel, you know, somewhat uncomfortable with these algorithms. This is stuff that you haven't thought about in a long time. So sit with that uncomfortability and see if you can learn something from these strange algorithms that we're talking about in this section. All right, I will see you guys soon, and I hope you have a great day.